Okay, so section 1.1, vectors. So Euclidean n space. So this is different than what you know as numbers. So in school, in like elementary school, you learn numbers. Those are real numbers. At first you learn counting numbers, right? So, you know, 1, 2, 3, 4. Then you learn about 0, that's whole numbers. But all of these and all the decimals in between these numbers are called real numbers. And the symbol for real numbers that you don't learn in elementary school, but the symbol is like an R with a sort of a double line. Have you seen that before? When we talk about domain and things like that, you'll see that R. Now, what linear algebra is, instead of R, just a real number, we're talking about 2 or 3 or 4 real numbers together. And they put a fancy bracket around it and to hold them together, but that's all it is it's extending what we know to a new sort of number system. So R2, it's like, looks like a squared, but it's not read that way. It's not R squared, it's R2, is a vector with 2 real numbers. So the way we see vectors is usually with a square bracket, okay? We also can see them with like a little triangle bracket, okay, like that. So these are vectors. So a vector, when we draw a vector, instead of a real number, if you were to draw a real number, you draw a number line and put a point on it. That's how you would illustrate a real number. To illustrate something in R2, you need an X and a Y. So, but it's not a point. But to draw it, we sort of look at it the same way. This is X and this is Y, just like a number, a regular coordinate axis. But if we want to draw the vector, it's not a point. So if we wanted the vector, say 1, 2, we go 1 on the X and 2 on the Y. Okay, that would be the point 1, 2. The vector is a directed line segment. Okay, I'm just going to put like an exaggerated dot on each end and an arrow. So that's the vector 1, 2. But the hard thing with vectors is that the vector 1, 2 has infinite places that it can be, and it's still called the vector 1, 2. So what do I mean by that? Think of this little vector that I drew, this arrow, as something I could pick up, like a pen or a toothpick or something. And I can actually pick that up. And what's important is the slope of it, like how steep it is or how it's angled. But if I pick that up and move that somewhere else, anywhere else, it's still the vector 1, 2. The arrow goes in the same direction, and it's the same length, and it's the same slope, but it's not fixed. It doesn't have a place that it's stuck to. Okay, so that's what's different about drawing, say, a parabola, where you're given an equation and it has a set of points and it's stuck there. If you move that parabola somewhere else, it's not the same parabola, it has a different equation. Vectors aren't like that. Vectors can actually be picked up and moved all around, it's the same thing. Okay, so we'll talk more about that in just a minute, but let's just look at what R3 or R4 would be. So R3 would be a vector with 3 real numbers. So it could be written this way or this way. And R4, of course, at 4. We can draw something in 3D. We can't draw 4 dimensions. So anything bigger, R5, R6, we wouldn't draw. But you could still do some of the algebra with it, adding vectors in R4, or subtracting vectors, or multiplying vectors. We could do some of the algebra with it, but we wouldn't be able to actually draw it and see what it would look like if you did that. But R2 and R3 have representations that we can look at on a picture. So we will draw R3 later. I'll show you how that works. So a directed line segment. Has a start point and an end point. The arrow points to the end. Okay, so that's important because if you put the arrow the other way, it's a different vector. So the direction it points, which side the arrow's on is important and how steep it is, and it has both a beginning point and an end point. To find that, say you were given 2 points, you can find the vector between them. By subtracting. So what that looks like is a vector, say vector u. To show a vector, instead of just a letter u, we'll put a little arrow on top. That's a little vector symbol. So the vector u is given by the end point minus the start point. Okay, so a question might say, find the vector from point 1, 2 to the point 3, negative 4. And draw it. So whenever I put a little EX here, example, in the notes, this would be a good exam or practice question for the final. Then I'm going to write the solution in a different color. So when you go back through your notes, you can find the question by looking for the little EX. You can write that on a separate piece of paper. Then you've got practice questions, okay? And the answer's in a different color, so when you go back to it, you can find the answer and correct your work. But anything I do in class would be good test questions because I made them up and I make up the test, right? Whereas the practice questions from the homework, I didn't make those up because I didn't write the book. So the wording, if you're looking for wording for the final exam or for tests, it would be more like what I do in class rather than what you would find in the homework practice questions, okay? Okay, so from the point 1, 2, so the start point is the point 1, 2. Can everyone see that pink? Sometimes if I pick a too light color, let me know. So your start point, so our end point would be 3 minus 4. Right, and that says from the point to the point. So it's starting here and to the point, so it would end there. So to find our vector, it's called a direction vector, is equal to your end point minus your start point, in that order. So you do 3 minus 4 minus 1, 2. So how do you subtract points? Any guesses?
X minus X minus 1.
Right. So you subtract the 3 minus the 1, and then you subtract the Y values, and you write it as a new point. However, they were points when we were subtracting them. These are points right now, not vectors. So I have a round bracket, just like an ordered pair in regular math. Watch the brackets. These are round brackets. They're points, not vectors. If we were to draw these, it would just be a dot. Once I subtract them, I'm making it into a vector, so I need to change what the bracket looks like. Does that make sense? So the vector, you go 3 minus 1 for their first element, so 2, and then minus 4 minus 2. So 2 minus 6. And you could write it this way if you wanted to. Those are interchangeable, those brackets, but the round bracket means an ordered pair, like a point that you would draw on a graph. Okay, so here's the vector, and we want to draw it. So it's not very hard to draw because we have the start and end point. We would just draw the start and end point and the vector between it, making sure it's pointing in the right direction. So the point 1, 2, 1, 2, and the point 3, negative 4, so which direction does it point? So starts at 1, 2, and it ends, so the arrow, you're starting here and you're ending, so your arrow would point in that direction, that's the end. In the book they might call it a tail, the end point, and the head, or the, yeah, I didn't look in the book to see what they call it, but they might call it that, sometimes they do. So it's in this direction. What if you put the arrow the other way? Would that change this vector? Any ideas? Yeah, like if we subtracted the points the other way, how would that change this answer? The signs would be opposite, right? And that's a different vector going in a different direction. Okay, so here it is, the vector. Now I said that vector's not fixed there. Even though we gave it a start and end point, it's still not fixed there. So if I said, as a second question, draw the vector 2 minus 6, that's the one we just found, in standard position. Standard position means the start point is 0, 0, the origin. Okay, so that's what that means. So standard position okay, so what would we do for that? Yeah, and where would we end? 2, negative 6. It really is. This is saying, this is the direction we're going in. It's really like a slope. It's the rise over run, like that kind of thing. And when you're doing a slope, you would say, go over 2 and down 6. And that's how this goes. This is the x. So go 2 in the x direction and negative 6 in the y direction. So we go 2 in the x and negative 6 in the y. So 1, 2, and 6. So the vector itself, and this vector up here, is also 2, negative 6. Same vector, but in a different position. Doesn't it look the same? Remember, it's like a toothpick that you can pick up and you can move it around. So we just moved it to a different spot. How would we move it to a spot that's not the standard? I already answered that, actually. This ends at 2, 6, but if it wanted to start it at a different point, you would start at that point, go over 2, and down 6. And that would be your end point. So that might look something like this. Yep.
Question for the sample 1.
Yeah.
First example. I see you use a different graphic style for the last several steps, right? So is that necessary?
Here?
Yeah.
So these were points, and a point, Like when you draw a point on a graph, that's a round bracket. So these were points. And then once we subtract them, we've made a vector. So then we have to switch the brackets to a vector bracket, either this way, with the triangle brackets, or the square brackets. Yeah. And that's really important. If you keep the round brackets, your answer's wrong. Because now you're saying it's a point, like a coordinate point, and it's not anymore. It's a vector once you subtract them. Okay? Does that make sense? So that's actually really important, so not a bad question. So here, if we start at the point 1, 1, all you would do to draw this is go 2 in the x direction. So 1, 2. What point, where would we be at 2 in the x? We'd be at 3. And then we're going to go minus 6 in the y direction. So from 1, 1, 2, 3, 4, 5, 6. We would go down to negative 5. So 2, and then down 6. And that's still the same vector. It should still look the same as all the other vectors. We just picked it up and moved it to a new spot. Right? So you can take a vector and move it around in that way, and you find your endpoint. What I often do if I were asked, like, say it gave you the direction vector in one point and asked for the other point, then you can always set up your equation vector equals end minus start. These are round, this is not round. Okay, so you can rearrange that. If you know any two of these, you can rearrange it to find the third, right? So you don't actually need to draw it to find the end point. If it asked you to draw it, of course you would, but if all it asked for was what's the end point, you could take your vector and your point and plug them in here, and you would just rearrange and solve and get the same thing. Okay? Questions? So far, so good. Lengths. So a vector is, that arrow doesn't mean it goes longer. It's actually, like I said, like a toothpick. It has a length. When you pick it up and move it, it's the same length. It doesn't go longer. In real numbers, when we draw a line, the arrows on the end mean something different than in linear algebra. What do the arrows on the end of a parabola say mean? It means, I'm not going to keep drawing it, but it would keep going in this way forever. Does that make sense? Here it doesn't. In linear algebra, that arrow stops. It's the end point. It doesn't go beyond that, so it has a certain length. Okay? The length is fixed. So that vector that we kept drawing, 2, negative 6, has a length, and no matter where you draw it, it's never longer. We can make that vector into a line that goes forever, and we'll show you that later in another section. Section 1.3, we do that. But for right now, they're just short, whatever the length is, it doesn't go beyond that. This doesn't mean continue. Okay? So the formula for the length is, this is like a double absolute value bracket. So the absolute value of the vector is a squared plus b squared. So if we wanted to find the length of that vector that we've been drawing, then what we would do is say the length, I didn't call this u, but you can even put it like this. You can put a vector in those two brackets, and that means the length of whatever vector you're saying is equal to 2 squared plus minus 6 squared. So I mean, if you had a calculator, you could see what that is exactly. It's 6 point something, but... Oh, sorry, 2 root 10, if you want, or... Okay, so square root of 40. So square root of 49 is 7, square root of 36 is 6, so it's somewhere in between 6 and 7. That's the length. If you were to measure it with a ruler, that would be the length, if it was in centimeters. Do the double lines mean the same as the single lines? Do they put single lines in the book?
I've only ever used single lines, so I haven't.
It would, but more standard it is to use double lines, but there's no such thing in linear algebra as single lines, so I would say if you use single lines, it means length. Magnitude, length. Did you take linear algebra before, and they use single lines? Then I would say it's the same thing. Yeah, yeah. Yeah. In the book, I just looked now, they do use double lines, so, yeah. It might be like different people, if they've learned it in different places, you might go with what you learned the first time, right? So if a different book had a different way, then that would be fine. So if you mess up and put a single line, I won't mark it wrong. Yeah. Because there's really no such thing as a single line anyway, so it's absolute value bracket. So the answer is always positive as well. And this actually just comes from Pythagorean theorem. Like if we were to draw that vector, sort of looks in this direction. This is 2 and this is 6 long. All right, we went over 2 and down 6. And we wanted the length of that side. Do you see the Pythagorean theorem there? 2 squared plus 6 squared equals this side squared. So that's all it is. So it just comes from Pythagorean theorem, the length of the vector. So that's how you would find it. What about in R3? What do you think?
C squared.
Yeah, you just add a c squared. In R4, d squared, right? You just square each one and add them together. So say we said that, find the length of the vector 3, 0, 4. So the length (3 squared plus 0 squared plus 4 squared), 9 plus 16, you get 5. So the length of that would be 5. That was done on purpose. I gave you one that didn't work, so I want to give you one that worked. And it was easier for me to think on the spot of something by putting a 0 in it. Okay, so that's length, and etc. Like if you had a bigger one, you would do the same thing. Scalar multiplication. So scalar multiplication is, scalar means a real number, and in linear algebra we don't just say real number because they're all real numbers in and taken however many you want. The scalar is a single real number. So a scalar, let's say, is a single real number. So scalar multiplication is, say, taking a scalar, say C, and multiplying it by a vector. And that's how it would look. So a number in front of a vector. So maybe it would be like 2 times the vector 3, 4. Like that. So how does that work? Multiply 2, it's doubling it. You multiply both of them by 2. So this would be 6, 8. Easy enough. They could be fractions, or we see a lot of roots in this, because if we're going to do stuff with length later, we get a lot of square roots that don't work nice. So, you know, you could have 1 over root 2 times the vector minus 1, 3, 6. You just multiply your scalar in. So what do you think that does to a vector? Right, yeah, and the magnitude is the length, it's another word for length, and it increases or decreases. So it changes the length. So this would make it double. This would make it smaller by whatever that works out to be. Right, if it was, just pretend it was 1/2, so it would make half the length, right, if that was a half. That's 1/√2 of the length, right? So, for example, if we drew the vector 3, 4 in standard position, then 6, 8, well, I should have drawn that down lower. Is the vector doubled. Okay, so, and it lies right on top of the other vector. And we would say, so here's a stretch again from what you know already, these vectors are parallel. Vectors that lie on top of each other are parallel vectors. Okay, so we actually would say, so they don't look parallel in the sense that you know a parallel line to be working in real number systems that we already know, but a parallel line in linear algebra are lines that lie on top of each other, okay? Or in the same direction, or not in the same direction. So, like, for example, I would say 1, 1, and -3 are also parallel. How could you see that they're parallel by just looking at them? Yeah, if you multiply the first one by -3, you get the second one. If you were to draw these, they don't lie on top of each other, but they're in the same line, if you think of it that way. So 1, 1 in standard position, and -3, oops. So they're in the opposite direction, but they're still on the same line. Okay, so anything that lies on that line would be parallel to these vectors. Okay. What if we found the length of these two vectors? What would they be in relation to each other? How much longer is this one than that? 3. So if we wanted, let's call U the vector 1, 1, and we'll call V the vector -3, -3. So the length of U and the length of V I'm still on the page, right. So the vector v is square root of 18, which if we simplified it, 9 times 2 is 18. We can do the square root of 9 is 3. Square root of 2 would stay there. So this is root 2, and this is 3 times root 2. It's 3 times as long. Not negative 3 as long, because negative 3 is not a length, right? The length of this is like measuring with a ruler. Your length is always positive, even if it goes in an opposite direction. So the vector itself is 3 times as long, but in the opposite direction, and that's how you would say that if you were explaining it to someone. So in the same direction, the arrow is going the same way. In the opposite direction, it's the opposite. Okay. Vector addition. So vector addition, let's say we have a vector u and a vector v. I'm not even giving them numbers yet, okay? So here's a vector v and a vector u. They're not parallel. So if we were to add those, I'm going to show you what happens, because you have to remember that a vector can be moved around. I happen to start these two vectors at the same point in this picture, but let me pick up v and move it, okay? So I'm going to draw the same two vectors looking a little bit different, okay? So vector u I'm going to keep the same, but I'm going to pick up v and move it to start at the end of u. Those should have looked the same, but I guess they're slightly off. But imagine they're the same. So I picked it up. It's still the same steepness, okay? But I moved it to a new place. It's still the same vector. It has the same length. It's just like I picked up the toothpick and moved it to another spot. Where it ends, when you add two vectors, if you put one like this, move it, and you could have moved u to the end of v, it wouldn't matter. That would end in the same spot. This right here is the point at the end of u plus v. So if we were to draw u plus v, it's here. Now the way I do it, if I had two vectors, okay, just another example, little shorter vectors. If I wanted to show where u plus v is, I go u, and then add v on to there, plus v. This is your start point, is where you started u. The end point is where you ended with v. And that start and end give you the vector u plus v. So we actually say, we'll put numbers in here in a minute, but we say that this is the diagonal of a parallelogram. So what's that mean? If you took two, you just copied u in two places and put v in between them, then the addition of them actually gives you the diagonal of the parallelogram formed by those two vectors. So if we had let's go something like that. Just don't want them to be too close together. So let's say U is 1, 2, and V is 5, 1. So 1, 2, and V, whoops, and I put round brackets because I'm showing the end point, not the vector, the point. And I've just drawn these in standard position. Where is it going to be? Well, if we draw U at the end of here, that will be the end point of our addition. But we could just add them and see. So when we add U plus V, same way as when we did the vectors, finding the vectors. If you add two vectors, you get a vector, 1 plus 5, and 2 plus 1. So 1, 2, 3, 4, 5, 6, 1, 2, 3. Oops. So in standard position, this is the vector, U plus V. And you could draw those little arrows on them. Basically, another way to think of it, if you have U and then you add this on to the end, so you're here at U, the end of U, 1, 2, and then V wants you to go 5 in the x direction. So from 1, we go over 5. 1, 2, 3, 4, 5, we get to 6. And then we want to go up 1, so from 2, we go up 1 to 3. Okay, so you can do it that way. And that's what I was illustrating up here. You take U, and then on to the end of U, you add V, and that would be your end point, where you would end up. What about subtraction? What do you think? Let's see if you can do it with the drawing without numbers, okay? So, vector subtraction. Nowhere in any book will you see it called that, because it's actually addition of a negative. It's what they think of in linear algebra, but we'll write subtraction. This is called the additive inverse. So they're saying add the inverse, which is the negative, so add the opposite when you subtract. So they don't use the word subtraction. All right, so here we have a U, and here we've got a V. If I wanted to subtract those, you say U, and I want to go to the end of this and go minus V. What do you think that would look like? So it's called the inverse because it goes in the opposite direction, but it's still the same vector, but we're going in the opposite direction. So instead of going V, this would be adding V. That would be plus V. It's taking your V and putting it on the end. That would be adding V to U. If we want to subtract, we actually go in the opposite direction, this way. You see it? So minus, when we do a negative of a vector, it's the opposite direction. Remember when I did that minus 3, minus 3? So 1, 1 went up, and minus 3 went the opposite direction. So that's what subtracting V sends us in the opposite direction. So our start point is here. That's where we started U, and we ended over here. So the vector between the start and the end is actually U minus V. All right, so think of it as a toothpick that we can pick up, that little blue line right there, U minus V. If I put that on the original picture, where does it go between? So put U minus V onto the original diagram. So it's this way. If we pick it up, we have to keep the steepness. Where do you think it goes?
That will go to the tip of the...
Yep. My vectors may be a little shorter up here. It's right here. So it actually forms a triangle, which is a very useful thing. Sometimes you've got vectors and you want to form a triangle, you subtract them and that gives you that third arm or the third side of the triangle you found by subtracting. So if you have three vectors that form a triangle, the third one is found by subtracting the other two. Or vice versa, you could subtract these two and get U. You just have to watch the direction that it points in. Right, and how do we get the direction it points in? If it was U minus V, then it goes this way. Starts at U and goes in the minus V direction, just like we did here. And you could do that with numbers. But you really need to understand what it looks like. The numbers would help to solidify what it looks like. You could kind of draw it and say, oh yeah, it's this. And that's not drawn in standard position though. If I put that subtraction in standard position, if I put all three of these vectors in standard position, U, that means starting them at 0, 0, V, and U minus V, and U plus V, that one is not in standard position. If you want it to be on the picture as a triangle, you have to pick it up from the standard position and move it there. So its start and end points are actually at the tips of U and V. Okay, so here's what you're going to try. Find and draw three U plus V minus V if U is 1, 2 and V is 3, 1. So I want you to try that. So did anyone get an answer yet? So I set it up for you here. In real numbers, if I write something down for you to solve, like if I gave one of my kids something to solve and I wrote down 5 plus 2 or 5 times 2 minus 1, what do we call that? What would I say? Solve this problem, solve this, is a better word, equation. You're looking for an answer for it. Sometimes they call them a math sentence in elementary school. Here, it's not called, this isn't called an equation that you're solving, it's actually called a linear combination. Linear, because it's linear algebra, and combination is joining them together either by adding, subtracting, scalar multiplication. So a linear combination is just another word for an equation, so solve the linear combination. That's a really important word. It's like joining two linear, or more. You could put a whole string of them that you had to add, subtract, and use scalar multiplication for. Okay, so if we were doing this, you multiply the 3 by both, so 3, 6, plus 3, 1. Then you add corresponding entries, so 3 plus 3, and 6 plus 1. So it says and draw, so what might we want to draw? I would definitely be more specific than this on a test. Draw U, draw V, and draw the linear combination. All on the same graph, in standard position, right? So all of that would have to be said. But where is U? I need to go 6, 7 is the biggest. So let's 1, 2, 3, 4, 5, 6, 5, 6, 7. So 6, 7. This is the vector 3u plus v. Right? Now let's put u and v on. U is 1, 2. And v is 3, 1. Oops. V. Okay. That's the drawing. But let's show the linear combination by thinking of these as little toothpicks. So if you wanted 3u, you wouldn't actually draw just one u. Because 3u does what to u? Makes it 3 times longer. So we would have 1, 2, 3. U, U, U. Isn't that 3u? And then what do we want to do to 3u? Add v. So at the end of the 3u, we're going in the v direction. At the end of 3u, we're going in the v direction. So it looks like this, which is what? Over 3 and up 1. Over 3. Oh, I did something wrong here. Let's see. 1, 2, 1, 2, 1, 2. Well, and so over 3. Where am I? Oh, I see what I did wrong. Hopefully you didn't do it wrong. Or did you just do what I did? I'm just going to draw it bigger. Okay, let's put u in accurately. 1, 2. So if I want to draw another u on the end, I didn't go over far enough. I need to go over 1 and up 2. It's just my tick marks weren't even. So over 1 and up 2. So u, u, u with the ruler would look better. But every time I have to go over 1 and up 2. Right? And v is what? Over 3 and up 1. Here's v. So I go over 3, 1, 2, 3, and up 1. There's v. So this is 3u plus v. 3u plus v gets us to this point, which is the point 6, 7. It's a vector 6, 7. Which is the diagonal of the parallelogram because we're adding. If you were to use 3u as one of the sides and v as the other side. right? So when we add, it gives us the diagonal of the parallelogram. All right, and what does minus v look like? We actually did it already, but I just wanted to. So that's minus times 3, 1. Minus 3 minus 1. So if we were to draw v, and minus v, whoops, yeah, that's right, minus 3 minus 1. Minus v, and that's just regular v plus v. All right, they go in the opposite direction, but if you had a ruler, they would be on the same line. Okay, so that's what that does. Okay, what's the time?